Hi everybody, welcome back. Well, things have been pretty busy at work, so I haven't had a lot of time to play at the bench. But I thought today I would just show you something here that was pretty interesting. I was doing some repair work on it. I picked this thing up a couple years ago and really haven't messed with it. And it had been serviced by somebody in the past, and some of the work on it was not very good. There were flying leads and components flapping around, so we cleaned it all up. And I just thought I'd do a quick show and tell on this, as I don't have a whole lot of time for videos this week. But I thought this would be something interesting for you to see. It's not really a tutorial how to use all this, but I just thought it'd be something interesting. This is a Triplett Model 3490A transistor tester. And the purpose of it is to test transistors. How about that? But unlike the little tiny ones that you see now that you can buy readily available on eBay or Amazon or any other place out there, this is capable of doing a much more extensive test. Now, you've heard me and even seen me demonstrate the curve tracer. And the advantage of a curve tracer is that it allows you to test a transistor at different input base voltages and base currents, I should say, and measure the collector current and generate the different curves for the HFE, or the forward current gain. It lets you see the performance of the actual transistor throughout its range of base and collector currents. This is a very similar thing, but instead of using an oscilloscope screen and drawing the curves out, you actually use these 3 meters to measure the outputs directly with different inputs, and then you can kind of plot a little chart. It's a pretty interesting thing. So it's a curve tracer without the curves. You generate the curves with a pencil and graph paper. So I'll just give you a quick rundown how it works. Now, the first thing this can do is it can test leakage current. Both the collector emitter and the collector leakage current, base current, and that was important a long time ago, because all germanium transistors, the old germanium jobs, they had a certain amount of leakage. And that was always a big problem, because you had to deal with that in the circuit design so that the transistor didn't go into what's called thermal runaway. And these are things you could look up online if you're not sure what I'm talking about. But with modern silicon transistors, which is what we see nowadays, that's not quite as much of an issue. But this is still a really good piece of test equipment, albeit it can be very complicated to use if you don't understand it. If you're testing transistors, especially high-powered transistors. So instead of just prattling on about it, let's plug a transistor in, and I'll kind of show you how it works. So the first thing we want to do is we have a 2N3055. That's just a very generic NPN power transistor. It's rated at 115 watts. I think the maximum collector voltage is somewhere around 60 volts, I think. And I think the collector current is somewhere in the, I don't know, 10 amp range or something. I'd have to look it up on the data sheet. But it's a very common power transistor. So this is the connector where you put the device under test. And you can see emitter, collector, and base is right here. And then you have a TO3 transistor input here with the little socket. And these two connect to your collector, because the collector is on the case of the transistor. And if we set this up, it's an NPN transistor. One thing you don't have, this may remind you somewhat of a tube tester, but it's not. In a tube tester, you get a nice big chart, a big manual, and you look up the type of tube you have, for instance a 6L6 or an EL34, and it tells you how to set all the knobs. This one, you have to understand how the device works, and it helps to have a data sheet for the transistor that you want to test. And you have to look in that data sheet, and you have to look up the certain parameters that are typical for that transistor, then you test it on this and verify that. We're not going to do that today because this is just a quick show and tell video, but I'll show you one of the things we can do. We can check both DC and AC beta, and don't get all excited about the AC beta. I'll talk about that in a minute. So the first thing we want to do is we want to set this thing. To check DC beta, we set the knob to DC beta HFE. There's a reason for all this in a minute. The collector knob we turn into these ranges here where it's reading. And essentially what we're doing is, if you notice, there's a scale or a range of current that we're going to apply to the base of the transistor, and we read that out over here. When testing the DC beta, what we want is we want to set it right here to this little line, and we want to set this to the 300 microamp range. So you're essentially going to have about 100 microamps of base current. And you're then going to apply an appropriate collector voltage, which is over here, and we're going to set the meter reading for the collector current to one of these ranges over here. And this will read beta up to 1000. And you could probably test the Darlington transistor on this, but you would have to do the math. But it's not hard to do. Now, if you look here, if we're at the 1000 rating, okay, so that would be for a beta of 1000, then that means full scale, where it says 10, would be an HFE of 1000. And for instance, this would be 800, 600, 400, 200. So that would be a pretty high range. And you can see that also correlates, if you look at the meter over here, to 100 milliamps. So essentially, if we set this meter over here to 10 microamps, or 100 microamps, and we set this to 100 milliamps full scale, you can see how it's going to read. Because really, that's what it is. I mean, the gain is the amount of current you're putting on the base, the ratio of that versus the amount of collector current that you get out. So let's demonstrate. So we'll turn this on, and these little transistors don't have super high gain. So I'm going to turn this one into the 300 scale, or the 30 milliamp scale, which means we're going to use this bottom meter reading from 0 to 30. We're going to times it by 10. Okay. We're going to set our input current for 100 microamps, which is going to be right here. And we're going to set our collector voltage somewhere around, this transistor is good for about 60 volts. I'm going to put about half of the voltage on it. So there's 30 volts right there. So we're using this scale, 6. So it's 30 volts. And right there, it already begins to read out. Now, this bottom scale, you have to times it by 10. So we have 10 right here would be 100. I'll zoom you in a little bit. And I'll move the camera over so you can see better. And if you look, it's saying 110, 120, 130, 140. And if you're looking straight on, which I think you are, it's just a little over 140, about 141 or 142. So your forward current gain is about 142. Let's see if that's right. All right, we got this little cheapy thing out here, and this is one of those ones that you can buy online. It's nothing special. Some of them come in a nice case, and the cheaper ones don't even have a case. It's just the circuit board. They all work the same. And if we hit test, look at that. Your beta is 145. Pretty accurate, huh? So, you might say to yourself, why the heck would you want something like this when a little cheap $20 thing like this could do the same thing? Well, if that's all you want to test is at low power, you want to look at a very low power, you just want to use a low power test to check the beta, you really don't need anything more than the cheapy one. But what this thing can do is it can actually use this thing or apply power to this thing in a real world scenario. In other words, if you look down here, it's not direct scale like over here, but you can actually put some pretty high base currents, especially with very low gain power transistors, and you can read up to 30 amps of collector current. So you can actually stress test this transistor at high current. And that's what this big block of copper is for, it acts like a big heat sink. So if you wanted to test the transistor very accurately at its full power and plot a curve, write your own curve, just like a curve tracer does, you can do it with this. The other thing this thing can do, let's set it back up. All right, so we're still set on our 10. We still have our reading here. It can also put a 1 kilohertz sine wave, it's a very clean sine wave, believe it or not, onto the transistor in the base. And we do that by changing this to set B. So we're going to set beta, and you set it to this line. And then you have two ranges. You have a 600 range and a 150 range. And right here it's going to read the AC beta. And you're going to find that on this transistor, the AC beta is going to be the same as the DC beta. So we're in the 600 scale. So you have 100, 110, 120, 130, 140, about 145 right there. See it? So it's just a tiny bit higher. You know, instead of 141 it was reading on the other meter, I'm reading 145 on this. That's about right. And the reason that is at 1 kilohertz, you're really not getting into the transition frequency range of these silicon transistors. Even these old-fashioned styles like this 2N3055 have a transition frequency of almost 1 megahertz, which is very high frequency. So you don't really see the gain change unless you had a much higher frequency drive. This would be a much better piece of test equipment if it could put out like a 1 or even a 10 megahertz sine wave signal to test the beta, where you could vary it. Maybe someday I'll look into seeing if this circuit can be modified to do that, because that would be pretty fascinating, but I doubt it because of all the wire runs and everything. You'd run into all kinds of inductive problems, or reactive problems, I should say. But nevertheless, on the older germanium transistors, this does make a difference, especially the small signal transistors. By applying a 1 kilohertz signal versus a DC level to the base, you could actually see how the transistor performs under AC conditions. I don't know if that makes any sense to you, but I hope. But anyway, that's just a short idea of what this thing is and how it works. And hopefully I'll be able to do some more involved videos here in a little bit. But things have been really busy at work, and we're very grateful for that, because we can always use the work. And well, until then, I wish you all peace, joy, happiness, and good health. And I hope you just enjoyed this little video and this little moment at the bench. And we'll be talking to all you again very soon. I do have some neat projects I'm working on in the background. This is one of them. This is a prototype. I have a finished one that's coming up, and it may be something that some of you may be interested in. So until then, take care, and we'll see you again soon. Bye-bye.